So now that we have the rules for combining functions in all the variety of ways, we have to just figure out all the derivatives of the remaining functions. And you'll probably have noticed that we haven't done any derivatives of trig functions yet. So we're going to start with sine of x. Got to go back to the limit definition. So the derivative of sine of x, limit as h goes to 0, sine of x plus h minus sine of x over h. Now what? It's not true that sine of x plus h is just sine of x plus sine of h. But there is a rule that you might remember from your trigonometry days for angle addition, some formula for the sum for the sine of a plus b. And if you don't remember it, that's fine. You'll probably never need to use it again after today. But the rule is that the sine of x plus h is the sine of x times the cosine of h plus the sine of h times the cosine of x, and then minus the sine of x that we already had. There was really nothing else we could do with that, right? We have to figure out something about sine of x plus h. And so you're starting to see why before when we were computing all these, when asking you to do them on homework and so forth, we didn't give you any trig functions or exponential functions. They're not quite as straightforward in terms of the algebra. All right, so what can we do now? I see two sine x's in here. So we can factor out a sine of x from those two terms. So sine of x, and what's left from this term is cosine of h. What's left from this term is a minus 1, all still over h. And then what's left here, again, we're doing this thing where we break up the limit into two separate limits. What's left from this is sine of h, cosine of x, all over h. And now we can do something that we did a couple times before. As h goes to 0, does sine of x change? No. Sine of x is like a constant from the point of view of h going to 0. And as h goes to 0, does cosine of x change? Also, that doesn't change. So just like we did in the constant multiple rule and in the derivative of the exponential, right? In the exponential, we pull the b to the x out front of the limit. We can pull this sine of x out front of the limit. So we'll get sine of x, limit as h goes to 0, cos h minus 1 over h, plus limit as h goes, oops, we have to, what should I be pulling out of that one? I should be pulling out a cosine of x, right? So cosine of x, limit as h goes to 0, sine of h over h. Now let's see what we can say about these limits. As h goes to 0, what does cosine go to? Cosine goes to 1. So we have 1 minus 1, which is 0 over 0. That's one of our indeterminate forms. We don't know what that fraction is until we investigate it further. Here, sine of 0, 0, also 0 over 0, another limit that we need to investigate further in order to figure out what it is. So now what you could do, perhaps, is go ahead on your calculator and try to plug in values of h closer and closer to 0 and try to figure out what this limit is and what this limit is. But doing it on a calculator is just basically, making an estimate. It's not real proof. So we would like to try to evaluate these limits in a more formal, prove way. So we're going to do this one first. So leave some space in your notes here. We're going to figure out what number this limit equals and what number this limit equals, and come back and fill in the blanks here. For now, let's try to figure out this limit first of all. So what is the limit as h goes to 0 of sine of h over h? So I've drawn this picture for us here because, we know how to define, what are the two shapes that we know how to define sine on? Triangle and the unit circle. So I've got the unit circle here. That's a circle of radius 1. And I've made a triangle. And I've put my angle h down here. Today, by the way, is when we're going to finally see why, to my mind, the convincing reason that we use radians and not any other measure. So you can look forward to that. What this has to do with this limit of sine of h over h at the moment is you should be completely perplexed about. This proof, I'm sure in the old days, was much longer. It's now been condensed down to its shortest possible version, which is what we're looking at here. So let's see if we can write sine of h, because we're going to have to get a sine of h into this limit somewhere. Sine is what on a triangle? Sine is opposite over hypotenuse, right? And I have two choices. I could either use the small triangle or the big triangle. Which one will give us the cleaner answer? The cleaner answer will be from the small triangle, because in the small triangle, the hypotenuse is 1, right? So sine of h is opposite, which is the length AD. We use absolute value bars to denote lengths in a triangle. AD over OA. But then because OA is 1, because we're on the unit circle, that just becomes AD. Since we've done sine, why not do cosine? Cosine on a triangle is adjacent over hypotenuse. Again, we could use the big triangle or the smaller triangle, but the smaller triangle will give us a cleaner answer. Adjacent is OD. Hypotenuse is OA. But OA is 1, so we get OD. Since we've done sine and cosine, why not do tangent? So we know tangent is sine over cosine. So I could say AD over OD, but is there a triangle that will give us a cleaner answer for tangent? For tangent, it's the bigger triangle that will give us the cleaner answer, because if I do opposite over adjacent, the adjacent side is another radius of the unit circle, so the radius there is 1. So this is OB over OC, but since OC is a radius of the unit circle, that is just OB. Again, what any of these have to do with this limit is not clear yet. Somehow we're trying to get something about sine of h over h. That's what's coming now. I see 3 areas in this picture. I've got a small triangle, and then the area of the circle, and then the area of the bigger triangle. And I can put them in order. So I can write the area of triangle, and this symbol for once in our calculus lives actually means triangle. It doesn't mean delta. The area of the smaller triangle, OAD, is less than or equal to the area of the sector of the circle, OAC. I can see I was drawing my line too soon here. This is good radio. And then finally, the area of the bigger triangle, which is OBC. All right. So what's the formula for the area of a triangle? 1/2 base times height, right? So 1/2. The base of my triangle is OD, which we figured out is the same as saying cosine. So 1/2 cosine of h. The height of my triangle, my smaller triangle, AD, is what we figured out was sine of h. So 1/2 cos h sine of h. Let's skip the sector for a second and do the other triangle. Also area 1/2 base times height. So OBC. The base of the big triangle, OC, is how long? This is the unit circle, so that's 1 unit long. This is a radius of the unit circle. The height of the big triangle, BC, that's right, because what mistake did we make over here? I said I wanted to use the big triangle for tangent. Tangent is what over what? Opposite over adjacent, so I should not have written OB here, correct? I hope all of you watching at home noticed that. Good for you. So this should have been opposite, which is BC, over adjacent, which is OC. Sorry if you've been worried about that for the past few minutes. Tangent is opposite over adjacent, which is BC over OC. This is what happens when we shoot to an empty room. Normally we've got a bunch of people out here. They're all raising their hands. Stop, stop, Eric, you made a mistake. Didn't happen today. All right, that's BC. So the height of our big triangle is BC, which is tangent h. Now let's do the area of the sector. So the area of a full circle we know is pi r squared. And the radius of our circle here is 1 because it's the unit circle. So the area of our full circle is pi times 1 squared. But we don't have a full circle. We only have some fraction of it. So suppose that h were, say, 45 degrees. This is just to make it easier numbers. 45 degrees of the full circle, that would be 45 over 360, in other words, 1/8. So you would write h over 360 there, if you were using degrees. But I've told you that we want to use radians in calculus. So we're really going to have what fraction of the full circle? We're going to have h radians over 2 pi radians, because 2 pi is the full circle. If this had been a so-called 45-degree angle, that's pi over 4 radians. Pi over 4 over 2 pi is 1/8, because a 45-degree angle is 1/8 of the full circle. So let's see what happens now, how things will simplify. So these pi's will cancel. That's good. Every term has a 1/2 in it, right? So I can just multiply through by 2 and get all of the 2's to cancel. And now we've just got cos h sine h. And what's left in the middle? Just h, right? I think if we hadn't used radians, we would not have something nearly as nice. Tangent, we know, is the same as saying sine over cosine. So this is the same as saying sine h over cos h. All right. By now, you've probably forgot what we're trying to do. I think I've almost forgotten myself. What we're trying to do is to evaluate this limit as h goes to 0 of sine h over h. So what I've got in the middle is an h. That's good. I would like to have the h on the other side of a fraction from sine of h. So I would like to divide this thing in the middle by sine of h. But if I divide it by sine of h, I've got to divide the other ones by sine of h as well. So now this just becomes cosine of h. And this becomes 1 over cosine of h. And if you were worried about what happened if h sine of h were negative, you should be a little worried. But you're going to see that in the end, what would have happened if sine of h were negative, we would have flipped these inequalities. And if you were quick enough to realize that we needed to worry about that then, at the end, I hope you realize that we didn't actually need to worry about it because flipping the inequalities won't make any difference in the end. All right, we've almost got what we want. We want the limit as h goes to 0 sine h over h. We've got it upside down here. So let's take its reciprocal. Sine of h over h. If I take the reciprocal of one of these, I've got to take the reciprocal of all of them. So 1 over cosine of h. And the reciprocal of this is just cosine of h. Except, in an inequality, when you take a reciprocal, what do you need to do? You need to flip the signs, right? Because if I had, for example, 2 less than 5, 1/2 is actually greater than 1/5. And now we've almost got exactly what we want right there in the middle. All that's missing is the limit as h goes to 0. So I'm going to put a limit as h goes to 0 in the middle there. But if I take the limit as h goes to 0 of one of these terms, I've got to take it of all three. Otherwise, we might not preserve the inequality. We're almost there to figuring out this limit. The next limit will be easier. This thing in the middle here is what we're trying to figure out. So we don't know what it is yet. Let's figure out this limit. As h goes to 0, what does cosine of h get closer and closer and closer to? It gets closer and closer to 1. As h goes to 0, what does 1 over cosine of h get closer and closer to? It gets closer and closer to 1 over 1, which is 1. So the quantity that we are trying to evaluate is greater than or equal to 1 and less than or equal to 1. How many such quantities are there? There's only one. What is the only number that is greater than or equal to 1 and less than or equal to 1? It's the number 1. So what have we proved? We've proved that the limit as h goes to 0 of this thing we were looking for, sine h over h, is exactly 1. And 1 is about as clean as the limit of clean of a limit as you're going to get. And the reason we got 1 is because we used what to measure our angles? That's right, radians. You can ask yourself, if you didn't use radians, go through this same thing. Instead of putting a 2 pi there, put a 360 there. Go through all this algebra. You will not come out with this nice number 1. I think you'll come out with an answer of pi over 180. So what does that let us do? That lets us put the number 1 over here. Agreed? We still have to figure out what number to put over here. For that, we could draw another one of these triangles. But luckily, there's a shorter way of doing it. So let's try to figure out what's the other limit. The limit as h goes to 0, cos h minus 1 over h. So what can we do here? The limit as h goes to 0, Well, what do you think we're going to multiply here? What do we always multiply by in a clever way? Multiply by 1. So we could multiply by something similar to the conjugate like we did once before, cosine of h plus 1. Right? I've just multiplied by 1 in a way that may or may not help us. But you're trusting me that it will help us. So what happens on the top, when I multiply cos h minus 1 times cos h plus 1, we get cosine squared h minus 1. And on the bottom, we get h cosine h plus 1. And if you didn't remember that trig identity for the sign of a sum, that's OK. But I bet there is one trig identity you know. What is the one trig identity you know? I think you know that sine squared h plus cosine squared h equals 1, right? Let me just write that small down here so we can look at it for a second. Sine squared h plus cosine squared h equals 1. This, in fact, is a form of the Pythagorean theorem. I don't know if you're aware of that, but that's what it is on the unit circle. So if I solve for cosine squared h here, what do I get? I get 1 minus sine squared h. So this is the same as saying 1 minus sine squared h, that's cosine squared h, minus 1 over h cosine of h plus 1. What's going to happen? The 1's will cancel. And now we can see something. I hope you're noticing how many times this semester, and we're going to keep doing it this week, we use something that we just figured out. Do you see here that if I rewrite this sine squared as sine times sine, I've got a sine h over h? And we just figured out what the limit of sine h over h is. So let's do that. Let me write it as the limit is sine h over h. And then I'm going to have to figure out what's left over here. Limit as h goes to 0. I've got a negative sine h still there on the top. And on the bottom, I've got a cosine of h plus 1. We're almost there. We just went to all this trouble with this wonderful diagram and this whole thing. Oh, by the way, this is called the squeeze theorem. I think I forgot to mention that. You squeeze the quantity you were trying to find between two equal numbers. Therefore, it equaled both of those numbers, equaled 1. So we just used that to figure out that this limit is 1. And let's figure out what this limit is. As h goes to 0, sine goes to 0. Cosine, luckily for us, goes to 1. So we have 1 plus 1, or 2 on the bottom. So we have 1 times 0 over 2. What does that equal? 0. So this limit, the other limit, is 0. So I can replace this limit by the number 0. So finally, after all of that work, what have we figured out? The derivative sine of x is simply cosine of x. Nice and clean, because we used radians. So if you don't want to use radians, then you will not get the fact that derivative sine is cosine. The derivative sine will be some ugly constant out front times cosine. This, to me, is the convincing reason for why we use radians. And we have an applet now for you to play around with that will hopefully illustrate to you that same fact graphically of what we've just done here.